So this lesson is 3.2.3 and we are looking at orbit descriptions. Specifically in this lesson, we are going to evaluate different types of orbits and how we describe them. So first of all, let's do a little bit of hypothesizing. I want you to look at the image that's on the screen and I want you to pause for a second and I want you to think about the different items in these orbits. So we have a silver orbit, a purple, pink orbit, yellow, green, and red. And I want you to make a hypothesis as to which object will complete its orbit one time around first. Okay. If you guess the silver orbit, you would be correct. So if you notice, the silver orbit has the smallest orbit, so its period is the shortest, therefore it finishes first. Let's take a look at this one. So these orbits all have the same semi-major axis. That's a word you were introduced to in the last lesson. But the eccentricities and orientation around the Earth are all different. So looking at these, which one do we think has the shortest period? Okay, looking at these orbits, if we were to guess, given that the eccentricities are all different, but the semi-major axis is all the same and the orientation is slightly different, without doing the math, it's hard to tell, but I would guess that we're probably looking at either the green or the blue having the shortest orbital period. Now let's take a look at inclination. So inclination is the angle between the Earth's equatorial plane, so the plane that divides our Earth in half, and the plane of the orbit, so the angle at which it is on its tilt. Okay, so this is what describes the degree of tilt in an orbit. So in the image that you see here, the yellow orbit has an inclination of 5 degrees. The red orbit has an inclination of 25 degrees. The pink purple orbit has an inclination of 45 degrees, and then our orange yellowy looking orbit is 75 degrees of inclination. So with that inclination in mind, we're now going to take a pause. We're going to talk about ground traces. So think of a ground trace as if we have a marker hanging off of the satellite and it's touching the Earth's surface. And as the satellite moves about its orbit, it's drawing lines on the Earth's surface. Now, while that would be quite messy, it looks something like what you see in the image to the right. And the ground trace is the projection of the satellite's orbit onto Earth. After a full day, the ground trace of a satellite with about a 90-minute orbital period would look like what's in the image. So with 90 minutes to complete its orbit, we get a pattern like what we see in the image. Okay, so because the Earth is continually rotating below the orbit of the satellite, the ground trace actually eventually spans all longitudes. So that's why we get this kind of spread out wavy pattern. So now let's step back to inclination with ground traces in mind. So the inclination determines the northern and southern latitude limits of which the satellite orbits. So as an example, a satellite with a 45-degree inclination will have a ground trace ranging from 45 degrees north to 45 degrees south. You can determine the inclination of an orbit simply by examining its ground trace. So if we look back at our ground traces here, these do match the orbits on the previous slide. So if you remember, this orange one actually had our steepest inclination at about 75 degrees. And you'll notice that it has the the kind of tallest of all the orbital patterns. So now let's talk about some vocabulary. We're going to look at the names of specific orbits. So when we have an orbit with an inclination of 0, meaning it's across the equatorial plane, we call it an equatorial orbit. And then an orbit with a 90 degrees of inclination, meaning it's completely vertical, up and down, is what we would refer to as a polar orbit because it goes above our polar caps. So these are two different types of orbits that we have. We have an equatorial orbit. So again, that goes around the equator, super easy to remember. And our polar orbit, because it goes around the polar caps, same deal. So here's what this looks like in terms of a ground trace. Our equatorial orbit looks just like a flat line because it's just covering the equator. Now the polar orbit goes very high and very low in this zigzag pattern and eventually passes over the entire Earth. So what do ground traces tell us? Well, based on what we've already learned about orbital parameters, we can determine both the inclination and the orbital period from a ground trace. Now, inclination is determined by just noting the northern and southern latitudes in terms of the limit of the ground trace. Now, the orbital period can be determined using a simple calculation that we're going to look at on the next slide. I do want you guys to just really quickly jot down the 25 degrees west longitude and the 0 degrees longitude over here. So first pass, second pass, just make a note of that in your notebook. We're going to need it on the next slide. So here's how we determine a satellite's orbital period from its ground trace. So I want you to remember that the orbit of a satellite remains fixed in space and that the Earth moves underneath it. So that means it's following the same pattern and the Earth is just moving inside of that. So the westward regression of the ground trace is due to the rotation of the Earth. So that means anything that we have that's moving westward is due to the rotation. So we determine how many minutes it takes for the Earth to rotate 1 degree. So that is 1,440 minutes divided by 360 degrees. So that's 4 minutes per degree. Then we determine how many degrees per pass the satellite's orbit regresses on a consecutive orbit. So that would mean the equatorial crossing is typically the reference point for that. We'll use 25 degrees as an example. So how long does it take the Earth to rotate this many degrees? That's the period of the satellite. So we take 25 degrees and multiply it by 4 minutes per degree. That's 100 minutes. So the orbital period for this satellite in this example is 100 minutes. So now let's take a look at right ascension of the ascending node, also known as RAAN, that can be represented by the symbol omega. So satellites may have identical eccentricities, semi-major axes, and inclinations. Those are represented by E, A, and I, but they can still be oriented differently in space. So they can either be rotated or twisted around the Earth in different ways. So each satellite here starts out above a different longitude on Earth. However, the longitude can't be used as a reference point because the Earth is going to keep rotating. So that means our reference longitudes will change as the satellite passes. So if we look at the RAAN, the right ascension of the ascending node, that is actually the angle that's measured along the equatorial plane between a vector pointing to a fixed reference point in space, the first point of Aries, also known as the vernal equinox, and the first point of the orbit where the orbital motion is from south to north across the equator. So you can see where those are represented in the diagram. And then this point is called the ascending node. So here for these orbits, you can see that the pink orbit or purple orbit has a 0 degree RAAN. The yellow one has 30 degrees of RAAN. The blue is 60 degrees and green is 90.